Okay, so I think we are live. Let me just check that everything is working. I have an excellent connection apparently. So I should see myself very soon right here. Analytics. I'm gonna put on my chat. I'm gonna pop it out and I'm gonna put it on the left side of my screen just so that I can actually read chat while the live is going on. Okay, so welcome everybody to the stream. Today we're gonna be learning about SIMD. So in pure Rust, I'm gonna later on another stream use what we learn in this stream to accelerate both Python and R. So I'm gonna be doing a future stream where I apply all of these concepts to making very fast functions in, for example, Python, and very fast functions in R. I'm gonna try to keep it some kind of like that. That would be like my goal. So yes, I think we are cool. Let me pop out the chat here. Let me. Oh no, I don't want my history out there. I want to pass on why. I have absolutely forgotten how to use my keyboard. I'm still learning, so give me a little bit of a break. Awesome. There it is. I have chat. It's zooming in the YouTube studio as well. It's okay. I have chat right here. I think we can read it all right. And yes, so we are here. Let me just tweet out the stream so that people on Twitter have access to this really cool knowledge. I'm gonna stop showing my desktop for a little bit of a second and just show my face while I do this. Let me tweet this out, twitter.com or x.com. Sorry, I'm still an old guy. So let me just go here, log in. Oh my god, why am I? I'm live. I will be exploring SIMD in Rust with you guys. Hop in and paste the URL and post. Okay, tweet it out. Awesome. Cool. Cool, cool, cool. So I'm gonna show my screen again. Go back to the scene and show my desktop. Awesome. So, the current resolution is the expected video resolution is 1920 by 1080. I guess it's alright. I don't think I'm taking like way too much bandwidth in. It's alright. Okay. So we have this repo. It's on the description. That's where I'm gonna be working, and that's where let me first do a history clear. Yes, I do want to clear my history. There you go. And let me go into my projects videos, and I'm gonna mkdir SIMD and Rust. I misspelled it, but I don't really care. It's alright to misspell things. Awesome. So let me just go ahead and do a cargo init dot, and I'm gonna change the name of the binary because I don't really want it to be called SIMD in Erst. I want it to be called SIMD in Rust. Awesome. And let me just create a little bit of a README. So what are we going to be learning today? Today we're going to be learning how to use SIMD in Rust. So this is meant to be a starting tutorial, not really advanced, but enough to get most people started. This is not just a some example. We will try to do something a little more involved. Okay, awesome. So what's the problem at hand? What's my idea? So since I usually work in data engineering, the problem, one thing I do quite a lot is filtering, right? And typically you're filtering string values or also factor values slash enum values. So the problem at hand is that we have, so let's say we have a data frame with n columns that we want to filter by a single value, right? So let's say we have, and I don't know if I can do like a little cool drawing of a variable, but let's say col1 is like contains the values 1, 2, 3, 1, 1, 2, 3, 3, 3, 4, something like that, right? Let's say we have let me do G Control A, yeah, col2, col3, col4, and let's say this one has, let's change the values a little bit. Let's make it 1, 1, 1, 1, 1, 1, 1, 1, 3, something like that. Let's say we have on the other one, let's say we have 2, 2, 2, 2, 2, 1, 2, 2, 2, 2, something like that. And let's just set the last one to 4, 4, 4, 4, 4, 4, 4, 4, and 4. Something like this. We want to get the row numbers where the value is equal to, let's say, 1 in any of the columns. So this is kind of like what we want to get to. This is the problem I want to solve. So in R, it would look something like this. So just like to, this is not this. There you go, R. And let me close this. So in R, it would look something like df col1 is equal to 1, and then an or, right? Or where's the or? Df col2 is equal to 1, or df col3 dot dot dot. I think we get the message, right? So this is kind of what we want to make really fast. Awesome, 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 awesome. So let's say here how to run. So how to run this? This will depend on some compiler flags because we are gonna need to enable AVX2. We could do just SSE2, which would be alright, but I want to use AVX2. I think most CPUs nowadays support AVX2. So let me just search for what CPUs support AVX. Oh, where's the V2, right? So Haswell processors 2013 or newer, and for AMD 2015 and newer. So if you have an AMD CPU from 2015 or newer, or an Intel CPU from 2013 and up, you basically have AVX2, which I think should be most of you people. Awesome. So to run, we're just gonna do sh. This would be Rust C flags. Let me see, look it up. AVX2 on cargo. This would be Rust flags. and then cargo run release. We could do it like in benchmark mode, but I think let's just do the benchmark ourselves. Awesome. So now let's actually get into our code. So let's say we have our data frame, right? So struct data frame. This is just like to represent like a very generic data frame structure. And let's say we have inside our data frame we have our data, and our data would be a vector of, and again, this is not like the most optimal solution, but let's say we have a vector of vectors of i32s. Usually in a, how do you call it, in a data frame you would have named like perhaps a names attribute, right? Would be probably like a vector of strings or something like that, or you would just have like the structure predefined, which is usually what I do. But yeah, this is just for the example, right? So we have this vector, this data frame, sorry, and what we're gonna want to do is search over the different sub vectors, so the different columns, and find the values where any of them are equal to something. So let's just build a little implementation, naive filter implementation. So our naive filter implementation would take a reference to a data frame. So let's do a reference to df would be a reference to a data frame, and it would take a value, and this would be an i32, and this should return a vector of booleans, right? And this vector of booleans should be like true, false, true, 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 false, true, false, whether a specific value in a row should be included or not. This is usually how R and Python use filtering functions when working with vectorized values. So this should be very, very common to return like a vector of true, false, false, true, false, 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 true, false, etc. Cool. So first, let's create here like an nrow attribute just to, so this would be like let how you call it, like a mask is the like, no, I'm not gonna call it a mask because it would confuse with other things that we're gonna be writing. Let's call it should include, right? And should include must be a mutable vector, so vec with capacity, and this would be df.nrow. Right, we wanted to have the capacity of the whole number of rows inside our data frame. And now what we're gonna want to do is probably I mean, we could use like the more, how do you call that, the more like default ways, is that how you would say it? The more normal way, which would really is like map and iterator and iterate through the values and get what we want. In this case, I'm not going to be doing that because yeah, it's not what we're trying to do. So let's do a for loop for I in 0, 0, let's say for row, right? In 2df.nrow. And what we're gonna want to do is probably do a push of some kind. Yeah, a push would be okay, but what I'm gonna do first is I'm gonna resize the vector to have, so first comes new length, right? So df.nrow and false. So by default it should not include a value, so let's comment this. Where's the create the output vector and set it to false. So I'm not sure if I could make this into, df.nrow. I can do this perfectly. So this is exactly what I want. This basically, and I want to inline this macro. It's fine. So this is basically what I want, right? A vector with falses and that has the length of the nrow. And what I'm gonna do now is I would have to iterate through every column. So for call in, let's say at data frame df dot data, no dot data, right? Because column here should be a vector of i32s, right? So this, and then inside of here I can do basically row, well, call and then row, right? This should extract, so let value row value equals this. This should be an i32. It is. And now what we're going to do is should include. We're going to convert it into should include row will be equal to, will be or equaled, right? So let's make it let should row should be included. This is very verbose, but I would rather have it verbose than so it should be either the current value, or if row value, this is not row values, this should be row value, or row value is equal to value. Let's just call it result. So I don't know if this is very understandable. Hi, how are you? How are you? Am I spelling your name right? Ghislaine? Ghislaine? I'm not sure if that's how you spell it, but if that's how you spell it, welcome. If not, correct me. I'll try my best to not to butcher your name. So here we have a row value, right? This is our naive implementation again. Our result should be either the current value, which at the beginning should be false, or if it's true now. And now we will store the result back in the original vector. So should include row will now be equal to the result. And then at the end, we just return result. Oh, the should include. No implementation for bool i32. Okay, yep. I need to put parentheses around it to make it more obvious for the compiler to know exactly. Right, so let's test this out. Let's have, for example, our let mock data frame mock df equals a vector, and this vector, well, first data frame and let's put here, oh, why am I there you go. Data would be a back. I will initialize later. And for now, let's set an nrow of much as your volume is low. Okay, let me see if I can increase the volume of my mic. So is that better? I think that should be better. I don't want to make it like way too loud, so I made it a little bit higher. Let's. Okay, yeah, no, it's much. Okay, thank you. Yeah, no, thank you, no. And Vinek, thank you for the feedback again. I'm very like sound sensitive, so sometimes I'm like not very sure if I'm doing things right. Thank you for the feedback. Okay, getting back to where we were. Let's set, for example, an nrow now of 100 And for now, can I do this without? So if I do, for example, 5 columns, and in here set a row like 1, and then 100. Is this okay? Apparently it is. Awesome. Okay, so now I should be able to run my naive filter implementation, and I'm going to pass in my mock data frame, and I'm going to pass in the value 1. And I should be let result, and I should be able to print. And the result. Let's cargo run this, and I get a bunch of truths, right? So this is exactly what we were expecting. If we did something like I want to add some randomness, so let's create a function right here. Let's create a function generate random df. Let's have this, well, not a random df, but like, let's call it mock df. Data frame. Why am I messing up so badly? Okay, so let's generate a pattern that repeats. So let's have like 0. Can I have like 1, 2, 3, and then dot repeat? And repeat this. Creates a vector by copying the slice n times. Awesome. So let's make this a factor of 4 to make it like easier to repeat. And let's repeat it 25 times. So let col1 equals this. And let's change this to, let's have col2 be 2, 2, 2, 1. Let's have this one be 1, 2, 2, 1. And let's have this one be 3, 3, 3, 1. So our result should have like a repetition of true, 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 no, true, true. I think there's no 1 on the, okay, it should be true, false, false, true, false, false, true, false, false, because the 1 is always included only on the first and the last value of this repetition. Now we can create our data frame. Let's have the data frame here. Let's have data equals. No, I didn't want to jump. Let's create here a vec. I hate this. I always get confused with this new keyboard. So it should be here. It should be a. It should be col1, col2, col3, and col4. And our n row for now should be n row should be 4 times 25. Let's put this into constants later. But now we have a way to simply generate our mock data frame. Awesome. So we should see that pattern. We should see like a true, false, false, true, false, false. Oh, well, true, false, 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 true, false, false, true, true, false, false, true, true, false, false, true, true, false, false. This is what we expected. Awesome. So we have our little naive implementation. So now let's create some sort of benchmark. Let's create a constant rep. Sure. And let's have this repeat instead of 25 times. Let's repeat it 10,000 times. Just to make it like a little bit more interesting. Rep. Here we will multiply by rep. Yep. Awesome. It's still run quite fast. Maybe 10,000 is a little bit too little. Let's make it 1 million. Awesome. And we're not going to print a whole 1 million. So yeah, we're just not going to do that. To kind of benchmark how well this does, let's just do a for loop. For I in... we don't really need the iteration. In... Let's create a constant. Rep time. Rep... How would you call this? Like... bench iters. A number of iterations in the benchmark. Let's set this to, let's do 1000 runs. In 0 dot dot bench iters. And what we will do here is we're gonna have let mute time equals standard duration from sex 0, right? So we're gonna start with this. Then we're gonna have let start equals standard time instant now. And then we're going to do time. I don't know if we can do a plus equals on the duration, but I think we have start that elapsed. Yes, we can. Awesome. And then we can get the let average time equals time divided by bench iters. And let's just make it this a U32, since apparently to divide we need a U32. Awesome. And now we can print the average time. So average time would equal, well, we would print the average time. Let's run this. It's gonna run for quite a while, maybe. Started learning NBin, couldn't get solid setup for R. Too little information out there. So no, maybe I could do like a good NVim tutorial for R if that's something that people are interested in. That's something I would absolutely be willing to do. Okay, maybe I will run this with release, cargo run release. Because maybe I was... There you go. So the average time was 6 milliseconds, which it's not much, right? But this naive approach works really well. It took 6 milliseconds, but we can make this faster. So now we're gonna get into doing some SIMD. So I'm gonna take this loop and I'm just gonna make it like function. Let's put it up here so that we don't interfere with anything. Benchmark. Yeah, let's just call it benchmark. So benchmark should take the data frame, the reference to the mock data frame. It should also take the value, which should be i32, and it should also take a function, which should be a impl f function. The version of a call that takes a immutable receiver. Sure, and it should take something that implements function. Let bind unused parameter replaced. Oh yeah, I need to set the return value. Now we can basically copy all of this. Here, bench eaters, I would have to take it. And here, mock df, which is bdf. And here, this would be f. So the function we want to benchmark. So f would be a function that takes in a reference to a df, to a data frame, and an i32. There you go. And yeah, that's right, result, we don't really use it. We can just leave it right there. And value would here be value. Awesome. So we can replace all of this with and we should also add like a title, right? So title should probably be a string slice. And let's add it here, title, and let's add a pipe, something like this. So let's replace all of this with benchmark title. This would be naive, that's a naive solution. We would take in a reference to our mock data frame. It would take 1 as the value, and our function would be our naive implementation. What am I doing wrong? All right, it returns it back full. Awesome. There you go. It's running. Tried to get into it, but gave up. Yeah, and Vim is... You have to be willing to put in the suffering, right? Like it's not it's not easy to get into. It takes a lot of effort, but for me it was absolutely worth it. Amazing. So now we're gonna take this naive solution, right, and we're gonna turn it into a SIMD solution. So this would be a SIMD filter implementation. Amazing, amazing, amazing. And now it's gonna get, I don't want to say tricky. Tricky is definitely not the word, but we're gonna have to pay a little bit more attention. So if we go on Google and we look up, I'm gonna pass this on to the second screen so that we have right here. Intel intrinsics guide. There you go. We're gonna look up the intrinsics guide and look at this. Look at this madness. Void MM2 intersect I32, and we have a bunch of stuff, right? And this might be a little bit confusing and perhaps a little bit scary. Once you kind of understand what's going on, it becomes less scary, but it can be quite scary, and it was scary for me. So all of these functions do something. This Intel guide is really good because it describes what they do, and we're gonna just focus on the AVX2, right? So I'm gonna click here AVX2 here on the little filter, go to AVX2. This is what we want. So we want to use AVX2, which AVX2 is an instruction set. So they're instructions that actually run on your CPU. And we're going to want to do these exact same operations, but with SIMD. So before doing that, for people that don't know what SIMD is, I'm going to do a little bit of a brief explanation. So I think it's quite obvious in this for loop that we are doing, how do you call this? That we are, how would you say it? We are operating on a single row at a time. And this is quite obvious, right? So we have row value, result, and we write that row. So we're doing one row at a time. What we want to do with SIMD is basically do it at too many rows at a time. AVX2 allows us to do it for I32 values at 8 at a time. So that's what we want. We want to be able to instead of processing one row at a time, we want to be able to process about 8 rows at a time. So that's what we're going to be doing. And I'm going to try to explain all of these instructions. And I think we can search for it. So what we're going to do is that we're going to basically try to translate what we have right here, this little code block, into SIMD and try to search it and make it as understandable as possible. So the first thing we're gonna want to do is basically convert our value, this I32, into a SIMD structure. A SIMD structure basically looks like an array. So it's 4 times the same value, because we're going to be comparing 4 values at a, well, not 4, 8 in this case, 8 values at a time. So let's look up here. So how to load, right? So if I look up here how to load, I get a bunch of instructions, and I want to work on the 256 I ones. So this means 256 bits, right? If we are running an I32, 8 times I30, 132, or I32, which should be like an M256 value. So let's look up what instruction we could use to convert our single what do you call this? Our single I32 value into a SIMD object. So let me search here for which one is the one that we should want to use. I64 gather FI32. So this takes a base address. We don't really want a base address. We want to basically just take our I32 and convert it into what? Into a SIMD value. So I really do not see the one that I am looking for. So maybe load is not let me look up repeat. Nope. Let's look up for int, like all the ones that take in int. Let's try to look at the function signature and find what is the instruction that we want. So this one extracts, this one does a mask, this one does a gather. I still do not see the exact instruction that I want. Perhaps a pack function, but packing doesn't really sound like the one that I want. So let me see if I can find the actual instruction that we need. So this manual is a little bit hard to get around. So we can perhaps go ahead and ask something like some sort of ChatGPT or something, or we can try to go to the Rust documentation. Let's go to the Rust core arch. So we can find this in the core arch x64 one. So as you can see here, here we have a bunch of the same. This is so long. Where are the functions? Oh, functions. Here it is. Is this divided into multiple submodules? Modules x86-64. No. Okay. So let's go into functions. So here we should see the same ones we have here, but perhaps on a little bit of a more of a better interface. Let's make this a little bit bigger. Oh, this is way too big. There you go. Okay, so we can see here we have MM256, add, MM to broadcast. Broadcast 128 bits of memory, composed of 2-pack okay. Blend, cast. We don't really want to cast currently. Extract. So this loads 256 bits of inner data from memory into a result. This one does some more masking. I'm just trying to like make it as pure as possible, because these instructions are not necessarily easy at the beginning. Like once you read them, it's like, okay, I can read this, but getting started can be quite a challenge. So let's look up here, Control F. Let's do a Control F repeat. Aha. Entonces, set pack 32-bit width and repeat the element in sequence. Okay, so this is for 512. I want it for 256. And I only find this for 512. Where is the 256 instructions? For taking an I32. And all of them are going to have I32, right? Yep. Sets back 32-bit DST supplied values. My god. So MM256. There you go. I have all my 256 ones. Blend, broadcast, cast, seal, extract, gather. Returns the value from a slice at an offset. No. Load U, loads to 120 byte composer from memory and combine them. So this should, we are going to use this one. We're going to use it later. We're going to use some of these later. But I want to start with, this documentation is really bad. Oh, I hate that SIMD documentation. So let's see what Google gives us. SIMD, repeat value. Repeat value into M256. Let's see what Google is able to supply us with. I don't want to. I just want to get the first value. How hard is it for documentation to give me what I want? SIMD, let's say SIMD load a single integer. Let's see what you probably mean by using load SI128. But this takes in an array, and I don't want to use an array, right? We want to take it directly from the value. We just want to repeat it a bunch of times. Load values to SIMD. Yeah, this is really bad documentation, but it's fine. It really is. We basically want to focus on a function that returns an M256I value. And perhaps what we can do is we should have some sort of, how do you call this? Some sort of function. I think we can look it up here. I think we can do returns M256. Can we do that sort of search? Can we see what functions return this value? Is that something we can do? Z0 set1 epi. This is what we want, right? The set1. Okay, so let's do this. Let's do this now that we have the information. I had to read the example to get it. So, okay. So I'm going to go here and I'm going to import. Oh, I clicked the mod button there. Let's import use score arch x86-64. And this will only compile on x86 computers, right? It's kind of obvious, but just to make it very clear. So we're gonna import M256 set or set1 ep I32. Right? So this function should return from a single value an M256I. Awesome. Cool. So now what we're gonna do is we're gonna redefine value, or create a new let value x8, right? Equals M256 at end value. And this is an unsafe function, right? Yep. So we're gonna have to wrap it in unsafe block. Oh, so scary. There you go. It's fine to use unsafe. This is not an unsafe operation. It's just unsafe because we're working at the architecture level. We're working with intrinsics. I really don't know why this is considered an unsafe operation, but it is, and perhaps there are definitely libraries that do wrappers around this sort of stuff, but I found them hard to work with. Um, I'm still waiting on the how they call this on SIMD on non-nightly, like on stable, on portable SIMD. But until then, we'll have to do with this. Awesome. So now we have our value x8. And the next thing we're gonna want to or need to do is go through each row. But remember, we don't want to go through each row. We want to go through every 8 rows. So we can do that quite easily. How I like to do it is let mut I equals 0. And what I like to do is change this to a while loop. So while I is smaller than df.nrow, right? I copy all of this. And at the end of the loop, I do an I plus equals 8. Something like that. Am I missing something? Is there a syntax error for some reason? Where's the syntax error? I do not see the syntax error. Okay, and this one closes this one. Did I delete something? Oh, there you go. Right. So now I'm going at 8 steps at a time, right? So now, okay, how do we change this row value, right? To something that because we cannot index column 8 times at the same time. We're gonna need some intrinsics, right? So now let's go back to our manual and let's look for load. And now, now that we have now that we're kind of getting started, we can start reading. Okay, what does this do? This gathers 32-bit integers from memory using 32-bit indices. 32-bit elements are loaded from the address starting at base address and offset by 32-bit index. Okay, let's see what else we have over here. I32 gather PD. What does this mean? Gather double precision 64-bit. Yeah, we don't want floating point numbers. This is not what we are looking for. Yeah, I don't know why this is okay. Let's see, I32 gather PS, right? So single precision. Nah, this is not what we want. Oh, I64 gather PS. I64 gather. We want let's see. Gather 32-bit integers from memory using 64-bit indices. Are loaded from the address using the base address. Okay. Okay, we're gonna need something in this ballpark. So let's go into our code, and let's import some other CPU instructions. Well, other intrinsics. So let's do mm256, right? And let's look for gather, right? And I'm gonna make this big so that we can read the documentation. And let's go through it. So returns values from a slice. This one takes a what? This one takes some sort of value and offsets. Yeah, this is not what we want. Let's see what else. This takes an F32, but all of these take these offsets that I don't really want to do any scaling. I kind of just want to. Okay, so maybe this isn't. Let's look for load. Okay, so this one takes a pointer to an F64. No, a pointer to an F32. No, F64, F32. This one loads 256 bits of integer data from memory into the result. Okay, this might be what we want. This one take, yeah. So I think what we want is this one perhaps. Um, maybe we want this one, right? Must be aligned. So that there's a problem with the alignment. That's not. Let's. We cannot assume that the values are aligned. So which one is the non-aligned version? This one, right? So M250 MM256 load U. U means probably unaligned. Um, and this is the function that we want. Awesome. So now we're gonna have to do some unsafe operations, but they are safe. Don't worry. We're gonna be doing them in, like, we know our bounds constraints, right? We trust that df n row is what we actually need it to be. Um, Unsafe doesn't necessarily mean it's unsafe. It means that you are the one in charge of guaranteeing the safety. Awesome. So, now let's do let row values, because now it's multiple values, right? So this is gonna be an nm to and what we're gonna do is we're gonna take column, oh well, row, right? Column, row. Yeah, so we're gonna take the column, which is the vector of 532s, and we're gonna start at, where did I get row? Oh yeah, row from was, well, I was using row. I should probably use row here, just to keep. I'm so used to I. There you go. So now what we're gonna take is row dot dot. So we're gonna take a slice of row up till the end. We could also do like row to row plus 8, and this would be guaranteed safety, right? Because this does checks, bounce checks, even in an unsafe block. But I'm not gonna do it like that. I don't really care. And now we're gonna convert it into a pointer. So as pointer, and I'm gonna do it as at const pointer to an and let's import here the MM256. M256. Oh, what am I? Why did I click the mod key again? 256. And this one takes an M256 pointer, 256i. There you go. M256i. So this is what we need on safe. We need to do some pointers, like convert to pointers. But there you go. We basically took our column, we indexed from where we want to start, so from the row we want to start to up till the end, and convert it to a pointer so that we can use the intrinsics. Awesome. So now we have our row values. Now this doesn't work, right? We cannot just compare our row values to. So now we're gonna do like a comparison, right? So let comparison, and this would have, let's look for an instruction to compare equality across M256. So let's do equals, right? And as you can see here, we have M256 compare equals app I30 I16. So we're probably gonna need this one. It's basically gonna check for equality and return a mask. Awesome. All right. So, how would you say this compared to back 32? Okay. So what we're gonna do, we're gonna import this instruction. I really wish we could go down right here. So M256 equals what is this? CMP equals for I32. Awesome. Awesome. So we imported it, and let's run it. So this would be an equals, and we're gonna have to pass in two values. So our row values, right, and our value x8, and this returns a mask. Basically, what this is is basically a bunch of i32s that are either 0 or -1. 0 meaning false and -1 meaning true. So we're gonna then need to do like the transformation to a boolean at the end. But I mean, we can deal with that without much of a hassle. Awesome. So now we have our comparison, which should be this part right here. So now let's turn this into comparison. Okay, now we're gonna need to do this OR value. So we're gonna need to first load what is currently and should be included. So let currently should include, right? So we're gonna need this part. And for this, we're gonna do basically what we did right here. But instead from column, we're gonna take it from should include. But now there's a little bit of a problem. Should include is booleans, it's not i32s. So we're gonna need to tell it here, basically, that it's gonna be -1. -1 i32. And we can like do like const SIMD false equals -1 i32, right? And SIMD true would be equal to 0 i32. That's just how masking works. -1, because we're working on multiple data at the same time, so we need like a lot of alignment. Awesome. Okay, so now we have our should include, right? We have here our values as a pointer, and now we can actually do an OR. So we have a currently should include, right? Oh, but we cannot OR M256i values, right? So how do we do an OR? So let's look for here OR. OR. Compare equals, compares greater than. Where is the OR value? I don't see it. From you, SRL. Where is OR? And why is it not looking for the OR? There it is. So, M256 or SI256, right? So this does a bitwise OR, compute bitwise OR 256 representing integer data. Awesome. So we're gonna need to import that instruction. MM256, and I clicked again I hate that key. 256 or SI 250. There we go. So now we're gonna change all of this to MM256 or, and we're gonna take both of these as arguments. Unexpected token. What token was unexpected? Okay, it's fine. So now we're gonna want to store this back into what? Back into the. So now let's look for store. Store now load. I remember there's a stream mask load. How is it? How is this one called? Let's go back here. Let's look for load. Loads bits from data from like memory into the result. Right. So I don't remember how what was the one to store. Mask store, store spec 32, the memory pointer address. Yeah, so this one is MM256 store SI. So what this one takes is stores 256 bits of integers data A into memory mem address. Amazing. So that's what we're gonna need to do. So what we're gonna have to do is do and MM256 store. So we're gonna need actually a store USI because it's not necessarily aligned, right? So store USI. Amazing, amazing, amazing. So now let's do the MM256 USI. We're gonna want to start it. We want to sort it into should include row dot dot, right? So we want to start it from the row that we started and as mute pointer. So we're gonna want it as a mutable pointer, and as mute MM256i, so that we tell Rust that it should interpret it and cast that pointer as a and result is what we want to write into it. What token? Oh, I'm missing a semicolon. Amazing, 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 amazing. I need to set the value types for amazing. Awesome. So this is basically the same code as above, but working on 8 rows at a time. You might be thinking of something that, okay, we're working, but what if it's not a multiple of 8? So we're always gonna have to run on some. So what I like to do is I'd like to do row minus equals 8, because on the last iteration of the while loop it always sums up one additional value. So we're gonna do gonna add here a little comment that explains why I did this. So this will remove what was last iteration of the while loop. Amazing. And now we're gonna do another while, but this while is gonna be, instead of running at 8 rows at a time, let's run at what, 1 row at a time. I mean, you could do working on like 4 and like going try to SIMD it as much as possible, but I'm just not gonna do that. Plus equals 1. And now here we can just copy the same code from the naive solution. Where's my naive solution? Here it is. Amazing. The only difference here is that now what we're gonna want to do is, in order to make this possible, because we cannot bitwise or what we're gonna want to do is do as I32 and multiply this by -1. Why do we multiply by -1? Because -1 is the true value in SIMD, like on the masks. So we're gonna have to multiply by -1 so that it aligns with the trues and false over there. So if a true converted to an integer becomes 1, so 1 times -1 equals -1, and 0 times -1 equals 0, which is, this is exactly what we want. But we basically just use our naive solution. Okay, so our should include value has a little bit of a problem that it, what do you call it? It is I32, it is not Boolean. If we can work with the I32 directly, that would be the best. If not, I think we can do like an into iter map. And if you cast -1 to a Boolean, does that give you true or does that give you false? Let's try to cast it directly. So let's do VS bool and collect it. compare with 0. Yeah, sure. Consider using this. Also works perfectly. Thank you, Rust, for the suggestion. Awesome. So now we have our SIMD solution. Let's benchmark it. So let's do our SIMD filter implementation. Let's see if it's actually faster. So now we're going to want to run with the Rust flag. So I'm just going to copy it from the README. Let's see if it's actually faster. I'm actually not sure. So the naive one took 5.4 milliseconds. Let's see if our SIMD solution is any faster. Ooh, it took 9 milliseconds. That hurts. That hurts. That hurts. I think it's the conversion. Let's have it not return the result, just so that we can remove it here from the benchmark. And let's just remove here the vec full. Let's just, because I think the conversion to a Boolean is what hurts the most. This final iteration. Let's see if that's true. Because if not, then maybe we are doing something very wrong. Okay, maybe we are doing something very wrong. Maybe that wasn't the problem. Maybe the Rust optimizations are just really good and better than what I am doing. Okay, so I mean, we can like make this a little bit better by, for example, here we could do this like inline it right here. So it should include, we could do this so that we don't have to do like the extra operation. And the comparison, we could also do it in there, right? So that will basically remove a little bit from the stack, but that should not be the end all be all of the argument. Like, I find it really weird that we are getting worse performance. So what I'm gonna do is I'm gonna take this whole thing, I'm gonna put it on a separate function. I'm gonna put on a separate function, and I'm gonna call this SIMD filter compare and store. And this one should take the reference to, so should include should be a mutable reference to a vec of I32s, and the column should be a vec of I32s, also like a single reference. Yeah, because I'm scared that the Rust compiler is doing optimizations that perhaps in this case the problem scope is just way too simple. It makes the compiler just make better decisions than me. But and row should be a use size. Let's make this an let's keep it like that. Right. And of course the value. Right. So I think what we can do right here is basically SIMD filter implementation compare and store. You can pass here add mute should include add column. What other thing can, then comes the row, and then comes the value x8. What I think we can do is basically do this. What this should allow us to do is Control V, and actually, this we can just do it over slices. Actually, casting to a slice will actually be a better solution. So add mute I32 slice, add I32 slice. Awesome. Awesome, 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 awesome. And now we're gonna do, basically, instead of 8, we're gonna do 8 times 4, which should be 8 plus 12, 16, 32. Maybe this will work better. Let's see. I find it weird that it's not running better. I should take a look at the what? At the actual assembly that it's generating. It's because I find it really, really weird. If I run this one first, does that change the? I wouldn't think so. Like it wouldn't make much sense for me that actually changes something. Yeah, it didn't change absolutely anything. Okay, I will accept defeat. I will accept defeat. I've been okay. Wait, the naive wait, what? So this would be the SIMD version. Why did the naive version get slower all of a sudden? Okay, this is weird. This is really, really weird. SIMD version took 9.2 milliseconds. Our naive version should take, again, 5 milliseconds was the value that I saw. 10 milliseconds. That's really weird. It's really, really weird. I don't know why it became slower once I switched the the order of the functions. Okay, right, this one back full, right? Okay, this is very, very, very interesting. Row +1. Yep, that's pretty interesting. But I hope like the message of how to write SIMD got to you, even if the performance we saw is not what we really wanted. Perhaps the problems, like the problem scope was like maybe way too simple. Maybe I had to make it like a little bit weirder to make it like to make the compiler struggle in getting the clear optimization. Because I was thinking like, I mean, we could do this, right? The call value here, and maybe we can trick the replace it with should include. Yep. All right, the parentheses are no longer necessary. That's absolutely true. This is what I was thinking could be done. But I have no idea why running the naive one first makes it so much faster. I'm thinking perhaps something with cache locality, but let's run it again like that. It takes 5 milliseconds. So maybe in the benchmark we should do something different. Maybe this benchmark is not like the best way to do it. I take the elapsed time, I sum it, I take the time it took to run, and then this makes sense for me. This makes a lot of sense for me. Perhaps we should we should have like a warm-up time. over 2. Something like that, so we can have like some sort of warm-up time. Maybe that has something to do with it, but I doubt it. If you only take like the second half, 10 milliseconds for the -1. So it gets slower. It gets slower on the second iterations. Huh. Okay, I think we're getting like into very nitty-gritty like implementation details that perhaps are not like the best things to do, but okay, it's fine. It's fine, it's fine, it's fine. I think we got the point across. I think this works good enough. I mean, we definitely are gonna want a warm-up time, so warm-up. And let's have the warm-up be like this over 3. Yep, and I think we have a good benchmark to run. Why is it not running faster? I really don't know. I'm guessing the compiler is already doing SIMD optimizations. But understand that not all the time the compiler is able to SIMD optimize things. I think this is like just way too simple, and the optimizer was like, okay, well, I know what to do. But maybe sometimes it isn't that clever, and sometimes it's not able to actually do that. Maybe. I'm guessing. I'm guessing. I'm just like guessing, right? But yeah, I wish we would have had like a better what? A better way to do it. But I guess it is what it is. What we could do to try to get the compiler to not know what it is doing is perhaps use an enum and represent it with an i32. Let's try that out. Enum animal. All right. And let's have here wrapper i32. I think that's how you do it. And let's have cow equals 0. Yep, that's how you do it. Let's have dog equal 1. Let's have cat equals 3. Let's have bat, just to have them all like 3-letter, equals 4. Right. And let's have here a vector of animals. Again, awesome. Let's derive, copy, clown, equal, partial equal, and equal. Awesome. Yep, so here we're gonna want animal, cow, animal, dog, animal, cat. What was the other one? Cat, yeah. Cat and animal. Dog, cow, and bat. What was the other one? Bat. So this one is 2, 2, 2. So just gonna do 3. Animal, dog, and animal vet. This one is 1, 2, 2. Okay, so now let's switch this one to dog. Let's see if the compiler is smart enough to know that all of these are just numbers that we are going to be comparing. This one is 3, 3, 3. So this one is animal, cat. And this one would be animal, cow. Or let's just use bat. Right, and here let's have value. Instead of I32, let's have it be an animal. This one would also be animal. This stays the same. This stays absolutely the same. Here this would be animal. And column back animal. Right, this will be of animal. Awesome. The rest is the same. SI32. Awesome. And let's do animal bat. Let's see if this helps our case a little bit, adding like this little bit of complexity. If the compiler is able to optimize it away. If not, we can deal with it. Naive takes 10 milliseconds. Yeah, this is the exact same response that we got. And the other one is going to be like 9 milliseconds. Yeah, I was able to optimize it. Okay, I think this is like the conclusion for now. We got a little bit of an improvement. Not very much, but we got something out of it. My guess is the compiler is already SIMDing it away. Again, this returns back vol. Perhaps it's adding like a little bit of overhead, which I guess is there. So if we remove like this right here, and this should include from the naive approach, perhaps we can see some sort of improvement. But I don't know by how much, really. I'm guessing not quite a lot. Or not as much as I would expect. Yeah, 10.8 milliseconds for the naive one. For the SIMD, perhaps it's going to go into the lower 9 milliseconds. Yeah, lower 9 milliseconds. Yeah, this wasn't the improvement I was looking for. If we run it without optimizations, though, so I think we can have like profile dot release level equals 1. I think that's how you do it. I'm not sure. Cargo optimization level profiles opt level. Okay. Dot release. If we lower the opt level to, let's say, 1, slightly better optimizations, sure. And this, I don't need the Let's see how it runs with lower level optimizations. Okay, for the naive it takes 12 milliseconds, and for the SIMD we know it's gonna take about 9. I don't think it's gonna increase by much. It's 7. Huh. So optimizations made it worse? But that's almost a 2x improvement, right? If we lower this to 0, let's see what 0. Okay, this is taking a long time with no optimizations. Those compiler optimizations definitely do help quite a lot. Hmm. Okay, yeah, this is taking like way too long to run. My other way to make it perhaps better a little bit would be to inline always. Yeah, let's give optimizations back. Working without optimizations. Oh no 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 no! I messed up. I messed up so badly. Oh my god. I'm so stupid. Okay, so here in compare and store, this is not actually row. This is row plus 8. I'm reprocessing the data so many times. This is plus 16. This one's plus 24. Oh crap, why didn't I think of this? Right, I'm actually missing the processing of much of the data by doing it like that. So I would have arrived at the wrong solution. Yeah, it's not faster, but actually with cache locality and stuff, it's definitely not going to be faster. But yeah, I mean, we got what we got. What we could also do to make it like a little bit faster would be probably to parallelize some of the things that we are doing. So to parallelize this, we would have to go through every column and do some sort of, because one depends on the last one, so that makes it a little bit harder. But we could perhaps go ahead and do that. I really want to try this with no optimizations. But it seems like it's gonna take like just way too long. So let's make this instead of having the dummy data frame, instead of having like 1 million rows, let's set it to 100,000 rows. Yeah, I thought we were gonna get. I did this for my job the other day, and we got a 12x improvement on a search function. And yeah, it was a similar example. Not exactly the same example, but something quite similar. So I thought we were gonna get the same kind of improvements. But the one that I worked on was a little bit more complex of yeah, so 11 milliseconds compared to 16 milliseconds. Yeah, that's better. It's better. It's better. It's again, it's not what I wanted from this, but we got it. Maybe we got something, I guess. Okay, I'm not gonna complain. Yep, I'm just not gonna complain about this. I think we got the message across. Whenever you need to do SIMD stuff, I guess this is a good starting point on doing SIMD stuff. And yeah, I hope this was a good live coding session that you guys enjoyed. Perhaps on another one, I'm gonna research some sort of problem that is a little bit harder. Like perhaps there's some null value, right? And we want to ignore null values. I have no idea. I'm gonna look for a part two to make something that we can see a much better of an improvement on. But yeah, I have no idea why my SIMD solution is not working as I wanted it to. Yeah, row values. We can take this and put it in there and stuff it. I guess it's fine if we make this perhaps an unsafe function. Now I'm just like finicking around to see why I'm not getting the, but this shouldn't change absolutely not anything. Yep, there you go. Perhaps something I could do is let nrow equals df.nrow. I'm thinking about cache locality problems. Let's see what happens. And perhaps instead of running like 1,000 iterations, let's run 100 iterations. I think is enough to get a conclusion. 60 milliseconds, 12 milliseconds. I actually became slower apparently. I don't know. This is weird. Pretty weird. Okay. I guess it's alright. Can't have everything in life. Okay. I think that's it for the session. Thank you so much for watching and see you on another. Bye bye.